Hello?
Hello, good afternoon, Guillaume. We're just waiting for a couple more people to join the class so we can kickstart.
Okay, great.
Yes, hello everyone. Whilst we're still waiting for more people to join the class, you can just type in your name and where you're from or where you're joining the class from. So there's energy in the chat room. Just your name, where you're from.
Is Professor Tom around?
No, he isn't yet.
Okay.
Hi, Daniel. Hi, Chidima. Hi, Chris. Yes, hi, Genevieve. We're just waiting for a couple more people so we can kick the class off. Okay, our teacher is here. Good afternoon, Professor. How are you doing today? Okay, I think you're on mute.
We can't hear you, Professor.
Now you can hear me, right?
Now, yeah.
Okay.
Great. So would you like to share your screen and then I share my screen? Or would you like me to share my screen?
I'll share mine, yes, and then you can share yours. Okay.
Great.
Okay, share screen. What I want to share is this one. Okay, can you see the slides?
It's loading. Now we can.
Okay, perfect. Okay. Very good. Well, shall I begin?
Yes, please. Yes, please. You can go ahead.
Okay. So my name is Tom Dietterich, and I am Chief Scientist of BigML and a professor at Oregon State University. And I'm here with my partner from BigML, Guillaume Vidal. And so I will give the introduction to this, and then Guillaume, who knows all of the details of BigML, will give the details and demonstrate our product. So the agenda is as you see here, and so I'll begin with the machine learning introduction. So machine learning, I think, has been operating as a coherent academic field for the last 40 years. But you can really trace its history back to the very early days of artificial intelligence. Alan Turing, of course, in the 1940s and 50s, speculated about the possibility that we could program a computer to be intelligent. And the first work in what would be called machine learning was done by Arthur Samuel, who's pictured here, who was working at IBM at the time. And he designed the first reinforcement learning system to play the game of checkers, or noughts and crosses, and achieved a reasonably good level of performance. He wasn't defeating the world champion, but certainly much better than he himself could play. But aside from that work of Arthur Samuel and some also early work on the perceptron, which was viewed more as a neural network model of actual neurons, there was not much discussion of learning during the early days of artificial intelligence, from when John McCarthy led a group of scientists who met at Dartmouth in 1956. In the 1960s, there was a small amount of work, but almost everything was handcrafted expert knowledge being built into computers, or even just basic knowledge. I would date the start of machine learning as a field to 1980, when we held the first machine learning workshop at Carnegie Mellon University. And I attended that as a graduate student. I was just in the second year of my master's program, and there were 30 people in that room, so it was a very small operation, much smaller than Data Science Nigeria this morning. So then in the 1980s was when we saw the first flowering of decision tree type algorithms. And in the second half of the 80s, the introduction of Bayesian networks, or probabilistic graphical models, the founding of the Institute for the Investigation of Artificial Intelligence. So this is a picture of Ramon Lopez de Mantaras, who is the head of that Spanish national lab. The more recent history, I think you all know, is that in the 1990s, there was a group at Holmdel, a part of Bell Labs, and then part of AT&T Corporation, that was exploring neural networks. And Jan LeCun was one of the researchers there. And he and his colleagues developed the convolutional neural networks based on some work that had been done in Japan in the previous decade. So the ideas underlying machine learning have really come from all over the world, and now, of course, are extending all over the world and having a big impact. BigML was founded in 2011, and our goal really is to democratize machine learning, to make it very easy for anyone to use. We envision that the modern corporation or business many of its employees using machine learning technology, not just a small group of machine learning super experts, but really that we would like to empower anyone to be able to, for instance, drag a spreadsheet into our system and immediately get some insights from their data, as well as, of course, supporting the creation of machine learning powered application programs. At that first workshop, here's Richard Mikulski, my advisor, and Tom Mitchell, who's actually my academic brother. We both had the same advisor at Stanford University, Bruce Buchanan. Okay, so let's position machine learning within the scope of artificial intelligence generally. So AI, of course, seeks to develop software methodologies that let us build intelligent software. And this includes many areas of, for instance, planning and reasoning in logic or in probability, optimization, solving problems like games, and so on. Of course, natural language understanding, computer vision, and speech, and all of these things. Machine learning as a subdiscipline is, of course, one of the, first of all, is a humans learn, and so learning is part of intelligent behavior. But secondly, machine learning is a tool to support all of the other things that AI is trying to do. So now we see machine learning as a key technology in building speech recognition systems or computer vision or things like this. Deep learning is a subpart of machine learning. These days, it feels like it has, taking over the field. But in fact, if you look at what is practical, that is well studied and being commoditized, it is the non-deep learning part of machine learning. Deep learning is still kind of a frustrating technology. We wouldn't use it if it weren't so successful, but because it is time consuming to use, you have to tune hyperparameters and design your architecture. It takes a tremendous amount of computer, specialized hardware, GPU machines, vector machines, and it takes an immense amount of data. So it is not the kind of thing that we can put into the hands of any employee of a company. Whereas other techniques, such as decision trees, ensembles, boosting, and probabilistic models, are technologies that are much more mature, and we have a chance to democratize those and share those with the whole world. So the picture we like to present is that that over time we've been able to tackle more and more complex tasks, of course, as our computers have gotten smaller and faster. And so let's now zero in on in practice, what is machine learning? I know many of you in the audience understand this very well. But we can view it as starting with tables of data and then finding patterns in that data that support making inferences. And mean for us to have machine learning data that is machine learning ready, that we can use right now. Well, we need our data to be in a table where the columns correspond to features or fields and the rows are instances. The fields can be of many different types, of course, numeric, categorical, and so on. So let's look at an example. Suppose we had a data set about who purchased today on our website. So we have an identifier for a person, the country they came from, the city, the number of days since their previous purchase, the number of page views that they went to, say, on our site, and their long-term value as a customer to us, how much have they spent, and then whether or not they made a purchase today. And then the question is, well, can we, for instance, predict whether for other customers, whether they will make a purchase? So we can think of machine learning as a form of programming, right, in which we're given this data, we put it through a machine learning algorithm, and we get out a predictive model that can be converted into code and deployed as part of an application. Then at runtime, we have the predicting time, right? We're given a new instance. We can push it through the model and get a prediction, and importantly, a confidence that goes along with that prediction. So, of course, the most important distinction in machine learning is between unsupervised and supervised learning. In supervised learning, we assume that we have an objective field, that is our goal, the thing we're trying to predict. And if that is a categorical variable, as in our case of a purchase decision, yes or no, then this is called classification. I think the terminology goes back to thinking about biological classification, where you have, say, species of plants, and you're trying to decide what species does it belong to, so you're classifying it. If the objective field is, for instance, a dollar amount, then it's a regression problem, and we're trying to predict how much, for instance, a customer might spend. So we divide up the space into these 8 kinds of tasks. So the first are the supervised tasks, where we have an objective, and we've talked about classification and regression. Another area is time series, where you have a sequence of pieces of information or visits, data points. And that gets you into the classic problem of forecasting the next element in the sequence or the next 100 elements in the sequence. Unsupervised learning, as its name suggests, is everything that is not supervised. And so we can talk about clustering data into clusters of similar points. We can talk about anomaly detection, where we're trying to find points that are very different from the data points we've already seen, and that might be coming from some other process, say a fraudulent transaction instead of a normal transaction. Association discovery, or topic modeling. we'll briefly talk about examples of these. So let's consider a predictive maintenance application. We could formulate that as a classification problem, given our, say, an automobile or a laser printer or something. Will this component fail? We could think of it as a regression problem. How many days until this component fails? Which is we could formulate that as then something that's known as survival analysis. We could think of it as a time series problem. How many components will fail a week from now? Cluster analysis, which of the, if we have a company with hundreds of these printers, how can we cluster them into groups and that behave similarly? We can ask whether behavior is normal or whether there's something unusual about this particular printer that might signal a new kind of problem. And we might look for associations. What alerts are triggered together prior to a failure? If we were doing network security, again, we can think about many different things. For instance, we might be using anomaly detection, which is very common in network security, to say, is this behavior of this user or this computer process or this network connection, is it something that needs to be investigated as a potential attack? If we were doing web analysis, we might be saying, let's predict whether a customer will make a purchase today, yes or no. And if we were doing insurance underwriting, we might be saying, how much value would this benefit to our company if we wrote this insurance contract today? Well, why is machine learning really have become so prominent today compared to the past? Well, I think one thing is the digital transformation of business is leading to an abundance of data. And of course, the digital transformation itself reflects the growth of the internet and the tremendous reduction in the cost of computation. So each of us can have a smartphone in our hand or maybe a laptop computer available, and this becomes our portal into the internet and to conducting business online. The other thing, of course, is the maturity of machine learning techniques. And so it's typical to see in computer science that there's a 20-year gap between when techniques are first being developed and when they are really usable by industry. And so we're seeing that, well, we have between 20 and 40 years of history in doing these kinds of things. So I will stop there now and hand the presentation over to Guillaume to continue. But I could also answer questions you might have right now, if there are any. I think there was one in the chat, but let's see what it said. Oh, just hello.
Thank you, Professor. Do you see my screen? I shared my screen.
Yes.
Okay, great. So I'll carry on. The second part is about real-world machine learning, and I'll speak about typical topics that happen, interesting topics that happen in real projects. So first, people might think when we idealize machine learning, we think about the dream, which is we have a CSV, then we create a data set, and then we train a model, and then we get some profit. But that, of course, is not what happens in reality. So in reality, data is distributed across many systems and with different formats. And even if we have data, sometimes data is not even available. So then there's a lot of variety into data sources, and there are many questions that arise, such as how shall I put the data together? What should my machine learning ready data set look like? And how can I measure impact in production? How will it look in production, etc. So there's a big challenge in data transformations. And an example could be like, for example, self-driving cars, where we're used to see fancy cars driving on their own, maybe in online videos. And this could be the tip of the iceberg, because in the end, there's a lot of data work that is unseen, such as the data collection, feature engineering, data transformations, and then the modeling part as well. So, well, just we need to remember that there's a big importance in all the data transformations part, and especially so Professor Tom has explained about the modeling part, which is what we see on the screen now. There would be a training part first, so we would train with the data, we would train a model, and then there would be the predicting part at runtime. And this picture is what we call modeling. And in end-to-end machine learning, modeling is just one of the parts, probably the tip of the iceberg, so the fanciest part. But then there's also there are also other important parts, such as preparing and transforming data, and the operating parts, meaning putting the models in production and probably integrating them into specific applications so they can be useful to people who needs to consume them. So in that sense, every machine learning application has different steps that can be considered sequential. So first, we have the problem formulation. We need to define a precise goal for our machine learning problem, and we need to formulate exact questions. So for example, if we had a churn prediction problem, the first question would say, okay, I want to predict churn of my customers, but then we would need to get into more detail. So it's easy. The first question is kind of easy, but then getting into the exact detail is somehow also a challenge. So how much in advance shall I predict the customer is going to leave? And what does it mean for me that a customer leaves? Maybe does it mean that he closes his account, or maybe it means that he's inactive for 3 months. So I should define all those details as part of the formulation problem. Then the next steps are about data acquisition. So I should get the data, and it's probably spread it over multiple locations and formats, and which makes it complex. Once I have the data, I'll need to transform the data and put it together inside a machine learning ready format, as Professor Tom explained. It's like a tabular format where instances represent what I want to predict. So for churn prediction, every instance of my data set would represent a user, and then the attributes would represent information that would be useful for my predictions later. We'll see an example in the demo of churn prediction. After I have my data put together in the right format, the next step is feature engineering. So calculating metrics, thinking about the metrics that will allow my algorithms to get the right predictions. And this is probably the most important, the most relevant point. And once after feature engineering, the next part is about modeling. So learn from data, which is modeling and then evaluating models to find the best one. Once I have the best model, I'll need to deploy in production and make predictions. And after I make predictions, once I'm in production, I can measure results with real data in production. So those would be the steps that we have for a machine learning application. And those steps are somehow iterative, because somehow when I evaluate, results are not sufficient, are not enough, not good enough, I could go back to feature engineering or even to data acquisition. And the same happens in production when if I see that with real data, results are not satisfactory, I could go back and do more feature engineering or modeling, and even getting more data if necessary. So machine learning is iterative, and we need to remember that, as I said, feature engineering is probably the most relevant of those steps for a better model performance, so that the best the features I get, they will have more impact in performance than probably changing the models. Also, another very important and fundamental fact is that the quality of the data is directly proportional to the quality of the result. So if my data is not of good quality or doesn't represent, is not realistic, then the final results, or maybe the data is incomplete, I cannot expect good results in the end. So it's important to have good quality data. And then I will see also in the demo that it is possible to automate modeling optimization. So to pick the best model with the best configuration, it's possible to automate that. However, it's difficult to automate feature engineering. So feature engineering usually requires expertise in the domain and also in machine learning. So here's another picture about the iterative process. Maybe more an easier picture. So first we'll need to define the goal and the specific goal we want to reach, and then getting and transforming data, calculating features, modeling and evaluating, and then checking if we met the goal. If we didn't met the goal, we can go one step back, then maybe trying different models. If that doesn't work, one other step back, and then probably getting new features. And if that doesn't work to get to meet the goal, probably we'll need to get more data, maybe different kinds of data, or maybe more historic of data, but more data, trying with more data to see if we can reach the goal. And otherwise, if we cannot manage to reach the goal, we'll have to change the goal definition to something simpler that we can reach. Once we reach the goal, it's time to automate and deploy in production. Let's talk about efforts in the different parts of building a machine learning application. So there's this article that you'll have in the PDF. The expectation collected statistically in this article is as follows. So that people expect that optimizing the machine learning algorithm takes most of the time, and you can see the other parts in the graphic. However, the reality is very different to what people expect, and optimizing the machine learning algorithm doesn't take much time, takes very few time, especially because most of the things can be automated at the moment. And we can see that building the infrastructure and collecting data are the most important matters in reality. In general, we summarize the effort requirements as follows. So we think that the problem formulation takes 10% of the effort in general. It's more than we expect, and in general, it's good. It requires time to define a specific problem with all the questions and picking the right algorithms at the beginning and having a good idea of formulate the problem. Then what takes most time is all the data part, so acquiring, transforming, and calculating features. And then the modeling part only takes 50%, and also making predictions. 5%, sorry. I would say that depending on the predictions, this doesn't count. This doesn't take into account the time to build an application. Obviously, depending on the complexity of the application, the time will be and the efforts will be different. So this counts the modeling parts and the productivization parts. And finally, there's 5% of time to measure results as well. Another topic, changing a little bit of topic, is that machine learning end-to-end machine learning is compositional, which means that we will speak about different kinds of models, but in reality, when we go to production, models will be combined into workflows. And in general, the idea is combining simple models into workflows to get better performance. Depending on the use case, there will be different kinds of combinations. But in general, in productions, well, in end-to-end machine learning is compositional, to take into account. Another important topic is about measuring the impact in production, and there's a key machine learning assumption that forces us to measure reality, which is that we make assumptions about training data being as representative as runtime data, and which is probably never the case. So in general, we assume that features will be measured in the same way, and they might not. We assume that customer behavior will not change over time, and it will. And we also assume that customer behavior will not change in response to deploying the model. And there's a good example on that with churn prediction, for example, where if we predict that customers will leave, and we have a churn prediction model in production, and our marketing team is making offers to customers that are predicted to leave, then our data will be somehow affected by the offers. So our future data, once we deploy the model in production, will be will be somehow invalidated by the fact there is a model already, and customers might not leave as a without, as before, without any interaction. So we won't have any pure data about whether the customer is leaving or not, and this will affect our measuring and our future training of models. So in these cases, we'll need to save some data in Virgin. So maybe some customers, 10% of the customers, we won't have any action over them. So we can keep their data to train future models as well. That's one of the possible solutions over that. However, well, the reality is that runtime data distribution is very different from training data. So we need to take that in account. And for that, we need to retrain our models. So there are different strategies. One of the strategies, and it's simple to implement, but it needs it needs computational lost my English. It needs computational power, and it's expensive. It's training every day, training as much as possible. If you retrain every day, as Google, they use that strategy at Google, then every day your models will be up to date, and they probably will be more tight to reality. However, it's not possible. Sometimes it's not possible to afford this, and there are techniques to monitor change detection. So what we can do first is monitoring changes in the distribution of predictions. So if I monitor my prediction distribution, and at some point I see some changes, there might be something changing in the data, and it could be a good indicator. Otherwise, I could also monitor changes in the distribution of input data. For example, for instance, with anomaly detection, as in this graphic, I could train an anomaly detector with my training data, and then all production data could have an anomaly score based on the training data. And once I get high scores, it would mean that my production data is different from the one I had before, and I could generate alerts like that. Also, change detection models can be put in place. For example, we can use a classifier separating training data and production data, and labeling training data with old and production data with new. We could use a classifier to separate with the objective of classifying old and new data. If the classifier succeeds, so if we get a good evaluation over that classifier, then it means that old and new data are different, which means that we can raise an alert and there has been change. And another option without machine learning is just monitoring. If we can evaluate in production our model accuracy, or in general evaluating, we can inspect the evaluation metrics. And then when there are changes over the evaluation metrics compared to what we had in the past, when we trained the model, then it could be an indicator of change. In any case, any of those indicators of change could be good indicators to retrain the model. And also there's another topic about keeping a strategy to roll back the model to the best reason. So when we retrain, it's good, but however, it's good to have a plan B in case something wrong happens. I mean, maybe the results are not as good as expected in production in the end, and then being able to roll back as quick as possible is also interesting. Okay, let me go with the BigML introduction. First, let's talk about machine learning evolution. Professor Tom already described the machine learning history. So it started maybe in the 1950s. We started talking about it, and then in machine learning as it is, probably started in the 1980s, where it was more devoted to the academics and researchers. Over the years, scientists and tools appeared, programmatical tools appeared, and it becoming more at the product level, available to scientists as well and to developers. And time by time, when machine learning as a service tools appeared, with BigML started in 2011, machine learning with graphical capabilities and simplicity was also is also available for analysts and for business profiles. So that's where we are now. There are plenty of machine learning platforms, and in general they tend to make machine learning easier and easier. And we expect machine learning being a commodity. There's 2020 here, maybe a bit further, and accessible to everyone. I think it already is accessible to everyone, but maybe it will be simpler in the future, and we can think about it as a utility even further in the future. Like, for example, there's a good example with Excel. So what Excel did to matrix mathematics, that now anybody can do matrix mathematics, and it was a complex topic in the past. There should be tools in the future that do that with machine learning. And well, that's a little bit what our goal in the long term. So I think BigML is, what we say is that BigML is machine learning made easy and accessible for all. So BigML is a machine learning platform that expects to democratize machine learning. And the fact that a lot of educations, a lot of universities, 600 universities over the world are using BigML to teach is a good indicator that the platform is simple and easy to understand. What about our design drivers? So our platform is a cloud-based platform, so it is scalable. BigML.com is on Amazon Web Services, but it also works with different kinds of clouds, and there's an infrastructure that is fully automated and auto-scalable. And well, all the complexities of the infrastructure are abstracted away. So BigML is also consumable. As you'll see in the demo, it's simplified as much as possible. There's nothing to install or to configure because it's a web platform. So you just need the URL and to log in, and then you can access your resources. You don't need any programming skills to use the dashboard. And there are plenty of smart inputs. So data is transformed in the background to make your life easier. And there are plenty of things that are being done automatically and that are more flexible than they tend to be with typical tools. We say there is a smart model consumption because there's a lot of graphics and everything is made easy. And we'll see in the demo as well that there is automatic modeling. So it picks automatically for you the best model and parameters. And it's also programmable because there are the architecture is API first. So everything you'll see in the dashboard can also be done with the API, via the API. There's a backend with endpoints, and all the actions that we'll do can be done also programmatically. And we have, the API has different bindings from different languages. So there's Python, Java, Node.js, amongst others. And we offer different constructors as well. So in terms of predicting related to the API part, in general, BigML is stored in the cloud. So it can be, BigML.com is a public cloud, obviously with security and private data, but also private clouds exist. So for specific customers, they can have a private cloud on their own. But there is in the server side, so all the models are trained in the server side. However, the predictions can be also done in the server side, but also locally. So you can easily, without any need of internet connection, download a JSON. So all our models or resources are represented as JSON files, and via this JSON file, which is quite a simple format, it is possible to make predictions using our API. And also, we have different inputs. So we have the REST API. We also have the different bindings. Here's a Python example. We have BigMLer, which is a tool for the command line in Linux. And we even have Alexa, an Alexa utility. So there are plenty of ways of doing predictions, and especially it's interesting that they can be done locally without even an internet connection. In terms of BigML evolution, as I mentioned, it started in 2011, and over time, new functionalities were added up to, and I think in 2020, there's a big release expected with image recognition. So be aware of that coming soon. But well, year by year, there have been different capabilities added, and And you'll see the dashboard how it looks now. I won't be able to explain everything. I'll take 1 hour for the demo, and I won't be able to explain everything. So, but there's a lot of materials online, and if you're interested, you probably can find a lot of examples. Currently, we have 130,000 users with over 100 million models and 7,000 education subscribers. And that means, so BigML is free of use. You can create an account and use it for free, up to 16 megabytes. And we give free subscriptions to students, free pro subscriptions. So you could use bigger data sets for free as well. So take this into account and feel free to create an account and ask for your free subscription to use BigML if you like, if you're a student, obviously. Also, we have 6 patents, and we work with customers from all over the world and in many different industries. Let's go for the demo. First, I think, I'm not sure about the audience. So I think most of you will have an idea about what decision trees are. And in case you don't, there's this utility here. I don't have time to show it now, I think, but there's a very simple way. Here, decision trees are explained in a very, very visual way. And I recommend, if you don't know how decision trees work, I recommend you to go through this web. It's a very interesting web from R2D3. Very visual. So the first demo I'll do is about supervised learning, and I'll use a bank customer churn prediction data set. So the idea is predicting churn prediction. So the data set looks like this. Every row represents a customer of the bank, and we have different attributes. So we have demographic attributes, for example, like the country, the gender, the age, and we also have financial attributes such as the credit score, the balance, number of products, if he has a credit card, if he is active in a bank, or maybe the tenor, which might be a statistical value. And most importantly, what we have in our historical data, we have a churn attribute, or I think it's called exited in the data set. And this attribute tells us 1, if the customer left the bank, and 0, if the customer stayed. So the idea here is using supervised learning to predict whether the customer will churn or not. So this is a classification, as this is a discrete objective, a binary classification specifically. Okay, so I'll show you the platform. This is how it looks. I'll zoom a little bit, okay. I can go here. So first, I'll show you how to upload files in case you never used it. I have here my CSV files, and the bank customer churn is that one. So this is a CSV file that looks like the one I showed you, and I just need to drag and drop the file to my browser, and it gets uploaded in the sources tab. So as you can see, we have different tabs. We'll go through them over the demo. The sources tab is what we call the file connection. And in general, here I just drag and drop the file, but you can also explore your computer to find a file, or put links to remote files. We support different protocols, and there's even database connections. So here you have Google Drive and Dropbox, and we also have direct database connections such as Elasticsearch, PostgreSQL, MySQL, or SQL Server. However, well, I won't spend much time here. So here in the source, if I inspect my source that I just uploaded, we can see that we could configure the file format. So it's a comma separated value file, and I could configure here the file details and even the types from my attributes. Okay, really quick, I will create a data set. And at this moment is when the whole file is being explored by the tool, and several things are happening in the background. So there are statistics that are gathered. There are transformations that happen automatically to simplify the task. So this is the data set. Here already we can see that we have 10,000 rows, so 10,000 customers. And we can see that there are data distributions calculated. So in general, for example, here is the credit score. This is the data histogram distribution over our 10,000 customers, and we can see also some statistics, numerical statistics. And especially we can see that the data set is quite unbalanced. It's good that not most of the clients stay. So we have 7,963 clients that stayed and 2,000 that left. And the idea would be predicting whether they leave or not. So in general, I told you that things were happening in the background at that level. And for instance, text data is transformed into a bag of words. The language is recognized and there are different tasks done, but in the end, text data is automatically transformed into a bag of words, which makes text data available for machine learning. The same happens with categorical values that are encoded, and the same happens with dates that are decomposed. So just for you to know that all those transformations happen transparently, and well, I won't stay much again because the demo I think is interesting based on supervised learning. However, there are capabilities as well to transform data. So we could join data sets, aggregate data, merge data sets, etc., and even add fields with different rebuild functionalities. So we could normalize mathematic functions, and even there's a little way to write formulas even with an editor and compiler. Just really quick, so you know that if you need to transform, there are functionalities as well, but we're not going to go through it. So okay, if I look at my data, I can see there's a row number, and this won't help. So it doesn't have anything to do with the outcome of the churn. It's something internal for me, and also the surname, and probably doesn't have anything to do. Here we see it's a text field, and we could see the cloud for the text. So well, the surname of people should be probably anonymized, and we will also keep it outside of the analysis by setting the fields to non-preferred. As you see, the customer ID was set to non-preferred automatically already. Okay, and my objective fields, so my target fields is the churn already, which is the last one, and it's set by default. Let's create a model, okay? So I just uploaded the data and created a data set. Now I want to create a model. So you'll see that there are two up here. There are two different buttons with the menus. So this one is about data transformations. This one, the gears menu, is about configuring models. And the cloud menu is about one-click options. So you can see the models here. And in the cloud menu, if I click, there will be parameters by default, so no configuration. So here, what I'll create now is a model. And a model is what we call a model a decision tree. So I'll create a decision tree with one click without touching any configuration parameters. And now my decision tree is created, and you can see that there's a visualization tool for the decision trees, and there are visualization tools for every kind of model, and I'll try to summarize how this decision tree was built and how to interpret this visualization for everybody, even people who are not familiar with that. So in general, decision trees are built by considering the data and making different splits. So every split that we make with the data refers to a node of the tree, and every node will be divided in two branches, and depending on the split of the data. So the first node contains 100% of our data, so 10,000 customers, and the distribution is the one that we had before. So 78% confidence that the customer will stay. Okay, and then the first split, as we see on the right, in pink, the first split is about age, and it's about age over or not 42 years. So depending on so this split has been chosen by the algorithm to be the most discrete for our objective field, and then on the left side of the split, I have 28.9% of the data, so all the customers that are over 42 years old, and on the right side of the tree, I will have all the other customers, so the 71% of the data customers that are 42 or under. And every time there will be different splits produced until I am able, the tree is able to separate data as much as possible, right? There are end conditions, and every node will have a split, and the green nodes are the ones that don't have any further splits. So the green nodes are leaves. Okay, you see that there are nodes that don't have a split, but the truth is that we cannot represent the whole tree in the visualization, and we represent the most relevant nodes, and you can always click to see more detail. So I could click and expand the tree in different ways. However, well, it would be too difficult to represent the whole tree. So that's why sometimes when you have discontinued borders for nodes, means that you can click and inspect more detail. However, well, and you can also filter the representation of the tree by confidence. So we could somehow want to see nodes that have you can have confidence or also probability. Probability is the probability of each node. So here we have probability of, which is the distribution every time of the data. And we can filter data by probability also to see more or less nodes. Okay, so and when I put my mouse over a node, I can see on the right side of the screen, I can see the path and the conditions up to that node. Meaning, for example, if I put the mouse with the mouse over that leaf, I can see that the tree, if any instance goes to that leaf, it will predict that the customer will stay with a probability of 99.45%. And when we built the tree, this leaf had 216 instances, which represent 2.16% of the data. And the conditions to get to this leaf are when age is under 42, when the number of products is under or equal 2, when the number of products is greater than 1, so equals 2, when the balance is less than 24,000, etc., when the gender is female, and when the credit score is under 578. In that case, our model would predict that the customer will stay with that amount of probability. Okay, so that's how we could read that the decision tree, and how the decision tree would make predictions with a new instance. In every node, there would be a question. First, is my customer greater than older than 42? Yes, I go here. Otherwise, I go here. And making questions at every node until I reach a leaf, which will be the result of my prediction. Okay. Okay. I think it's clear, even I hope, for people that are not familiar with decision trees. So we also have other visualizations. For instance, an important visualization, especially when we have a lot of variables, is seeing the field's importance. So in this case, we can see that for our model, the most important field is the age, with almost 29% of importance. The second most important field for our model is the number of products that the customer has. Third one is the balance, and etc. So this is very helpful, especially when we have hundreds of features, and to understand which ones are more relevant and more important in building the model. Also, I can prove you, so I can show you how we can make predictions over that model. In general, once we have a model, predictions are done programmatically via the API into an application. So here we would build an application for marketing people. But just to demonstrate how this model can make applications, predictions, we can emulate a new customer for the bank. So we can emulate the age of the customer. So maybe raising the age to 51, maybe, and then the number of products that the customer has. We can see that increasing the variables or touching the variables, the prediction of the model changes. So this model is actually making predictions, right? In case you had doubts. And there are also other visualizations. This is the partial dependence plot, and I'll explain it later. I'll explain it with ensembles a bit later. And this is the sunburst, which is specific to decision trees. And as you saw before, the whole tree cannot be shown with the tree view. However, with the sunburst, it's somehow like the tree view, where this is the root of the tree. So we have all the instances in the middle, and the splits are represented according to the proportion of the data. So we have 28% of customers with less than 42, and 71 with over 32 years. So this is the proportion of this first split, and then we have the proportion of the splits that goes recursively. So we can color it in different ways. So the coloring that I have now is that the prediction result. So I can see 0 is blue and churn is orange. And by looking at this graphic, by placing my mouse on top of any square, I could get the insights or the questions that on the right. I can see that to get to that square that is churn positive, then it means that if the age is under 42 and the customer is not an active member, then I'll predict that the customer will churn. And this gives me visual insights quickly about what tree is doing. So maybe here I can see that the age under 42 and two products only is also providing churn with a confidence of 67%, and etc. So this is another view that we have for our trees. Okay, so now I have this tree, and I created a model. I was able to make predictions. However, I'm not sure if it's doing well. No, I mean, maybe is it doing well? I cannot. So there's the part evaluations, which is an important part in machine learning, and it consists of keeping some data. So now I have 10,000 users, and I could keep maybe 2,000 of them apart, and then build my model with 8,000 and check the results of my model, comparing the predictions of my model about the remaining users, the remaining customers, comparing the actual results with the predicted results, and then I would be able to see if my model works well. Okay, so the first thing I'll do is splitting my data. I'll use a linear split in that case. In general, there are random splits that are done, and I can change the proportions. 80-20 is the default. And then I have here my training data set with 8,000 users. And I'll be able to create a model as well, just as I did before, by clicking on the model option in the default menu. And it will create another decision tree. Okay, here I have it. It looks like the former one. We can look at the field's importance, the age, number of products, and balance, same as before. But there's a difference, I think, at the continuation, but looks good. And then what I can do is evaluate it. And then automatically it should select my test set. This time it didn't work, but I find my test data set over just with a few letters written. And so I'll evaluate my model with my 20% test data set that I kept before. So now it's making predictions over the 20% data set, and it's comparing the result of the predictions with the actual results. And sorry, here I wanted to show you the basic view first. And my positive class, and what I want to predict is customers that churn. So my positive class is 1. So I set my positive class to 1. This is the evaluation view. Most of you may be familiar to this. So this is a classification evaluation. And what we see here is the confusion matrix. And what we see on the bottom is several metrics. Maybe you heard of the accuracy is very typical, precision and recall, and others. Let me explain in more detail for people who are not familiar with that. So in our training data set, we had 2,000 customers, and here what is this metric is about? This matrix is about so in the rows I have the actual values. So I had actual exited, I had 390, and actual that stayed, I had 1,610 customers that didn't churn. Okay, and then on the columns I have what the model predicted. So the model predicted that 281 customers churned, and that 1,719 didn't churn. And what it is displaying in these squares is the count. So how much actual churn customers did the model predict that were churn? 192. Those are true positives. How much non-churn customers did the model predict that didn't churn? 1,521. Those are the true negatives. I have it here. And then the errors. So customers that actually churn and the model predict that didn't churn. 198 false negatives. And customers that didn't churn and the model predicted that would churn, we have 89. So this is the confusion matrix. It displays the matches over the different cases of prediction errors or successes. And we have the counts just besides. And then we have metrics. The first metric is the accuracy. The accuracy is the overall success rate of the number of correctly classified instances. So in total, we had 2,000, and from those 2,000, this case plus this case, so basically 1,720 something were correct. So in the end, this makes an 80% accuracy rate, which is the total we did right over the total max. So it's a percentage. Again, we have the precision and recall, which also are quite typical. So the recall would be over the actual churn customers. What percentage did I successfully predict? So there were 390 actual churn customers, and I predicted 192. So the percentage is this one. So over 192 over 390. And with precision, it's in my positive class. So over the predictions, churn predictions I made, what percentage are true? And so again, it's the percentage with the true ones over the total that I predicted, and it's a 68% in that case. Okay, so those are typical metrics that are used in machine learning, accuracy, but accuracy is not very reliable when the model is unbalanced. And then we have precision and recall, which are more reliable in general. We also, as you can see, we have the F measure here, which is a more complex and complete metric, such as the phi coefficient. Those ones are more difficult to understand, but it's as they are more complex and complete, they might be better to compare models. And for experts, so maybe beginners shouldn't take care of what I'll say. I'll show the advanced part of the evaluations, but please just forget about it if you don't understand and if you're not familiar with it. But experts that are familiar with evaluations, they can see that we have an extended view with the curve. So we have the ROC curve that is displayed, and then we have another metric, which is the area under the ROC curve, which is very useful in general. It's the area below that curve. Okay, and other metrics also appear within the advanced view. I won't get into much detail. We also have the precision and recall curve that is also displayed with the area under the curve metric as well. And note that we have a probability threshold. If I go back to the ROC curve, we have a probability threshold, and we can move the threshold at the emulating predictions at that probability threshold, and then we can see that we're emulating the precision. So all the metrics are recalculated based on that threshold. And the max figure, theoretically, the optimum threshold is marked also at that level. Okay, just a short comment over the advanced evaluations that we have for in case you are familiar with this. Okay, so I created I evaluated this decision tree, and maybe to show you a little bit more, we have different supervised algorithms. So we have ensembles that are groups of three, we have linear regressions, logistic regressions that also are useful to classify, and deep nets. It's about neural networks to classify and for classification and regression. So I won't show them all. I'll just show you the ensembles to see the difference between decision trees. So ensembles are groups of trees. So decision trees are sometimes poor. They are easy to understand, but sometimes have overfitting and do not give the best results. And a way of improving them is putting different trees together. And there are different ways of doing it that are supported in BigML. So if I go back to my training data set, I have here my 8,000 customers. I can now, so I was creating trees by clicking on the default menu. And if I go to the gears menu, I have the configuration appearing. So here I want to configure an ensemble, and then the configuration panel appears with different configuration options. Okay, I won't get into details. There's an automatic optimization thing if you don't want to take care about it. So you can just activate automatic optimization, and it will use different attempts with machine learning, so Bayesian optimization, to get the better parameters for your data set. Okay, that's one option. In this case, what I can do, for example, is so I can show you that we support decision forests and boosted trees, so we can emulate decision forests, such as the random forest, or we can also emulate boosting trees. In general, I'll keep a decision forest, and clicking on that button, I'll randomize. So it will be a random forest algorithm. So if this is not familiar to you, a random forest is a very famous algorithm. And well, by clicking on that button, I just created an ensemble. I'll create an ensemble that will have 10 trees, which is the default. I could increase the number of trees. It would be enough for now. So now it's creating 10 decision trees using randomization. It will be equivalent to a random forest of 10 trees. Let's see how it looks like. Okay, in this visualization, we could view the trees. So we have the 10 trees here, and if I enter, I could visualize the tree. However, combining 10 trees, it's not so interesting to visualize the trees one by one. And what we display in that case, and it's something that is available for all classification and regression algorithms, is the partial dependence plot, the PDP view. The partial dependence plot view is emulating predictions based on and displaying the prediction results by coloring based on two attributes. By default, the most important attributes in the model. So here it selected the number of products and the age. And I can see the prediction results of my ensemble. So I can see that when the number of products is over 2, customers tend, in my data, customers tend to churn. Churn is 1. And we can see that with the age, it's, we have here a section where it's mostly orange. So there will be churn as well, maybe with only 1 product and between 52 and 65 years old, they also tend to churn. And well, we could inspect with other metrics, or maybe using the balance. And if we wanted to introduce other metrics, so we have 2 dimensions, but we could introduce other metrics by selecting values here. So I could maybe use the active member. Okay, so this is for non-active users, and this is for active users. And well, there are ways to visualize data, to visualize the predictions of my my complex algorithm. In that case, 10 trees. So in this way, it's a good way of visualizing the outcome. Again, I have the fields importance, where we have the age, number of products, and balance. Again, as the most important. I think the geography is the 4th in that case. It wasn't before. And now I could evaluate my ensemble. So by selecting the 20% test data set that I kept before, I can evaluate my ensemble and see if the metrics are maybe better than before with my decision tree. So with my positive class to 1, I think it's a bit better. The precision is higher, and I could look at the curve. The curve looks better. I think ensembles always work better than decision trees. Okay, so but now I could inspect and compare both evaluations, opening them in 2 pages, or I also have an evaluations comparison screen where I could put here. I will have 2, but I could do it with many evaluations and compare them, putting them together side by side and seeing the metrics side by side to see which one is better. So we can see here. So the most it gets to that corner, the better. To summarize for if you're not familiar with that. So we can see that the blue curve is going closer to that corner. So it's better than the orange one. And the orange one, from that icon, the orange one is the decision tree, while the blue one is the ensemble. We can also inspect metrics here in a table at the bottom. So this would be a way to maybe try different algorithms manually and compare the evaluations and see which configurations work better. And based on that, pick a model that works better for my data set and that will work better for my churn prediction. Okay, and this is, in general, doing this manually can take time. So the thing is that we found a way to optimize it. There is automatic optimization. I showed you the automatic optimization in the ensemble configuration. You have this in every model that you create, in every supervised model. For classification and regression, but we have something that puts everything together, optimal. So let me configure one and show you. So we have optimal here, and optimal is going to try and test all the kinds of classification. In that case, is a classification, so it will be classification algorithms that BigML offers with all the kinds of configurations. And based on that, using also machine learning in the background, it will results after a few minutes, or depending on the case, depending on the data set, it can take a few hours as well, and result with the most performing model possible without any manual interaction. So we wouldn't need to do all the work ourselves. And here, what I can configure, so to show you how simple it is, there are time. I could change the execution time or the number of candidates to somehow change the execution. So somehow parameterize the execution times. But well, in terms of modeling, I could discard, for example, decision trees because I might know that they will perform less worse than ensembles. I'll leave them open. And then in terms of evaluation, I could select a holdout, as I did before, my 20% data set. But in this case, I won't need it because cross-validation is supported. So cross-validation will do several evaluations by splitting the data set in different manners randomly. And then I will select what metric I want to optimize. The raw KUC is a very good metric to optimize. And I will tell him also my positive class. So what I want to optimize is the raw KUC with a positive class 1. Which is churn, which is what I want to predict. And then I just need to push the button to create the optimal. And as said, this will take a few minutes with a small data set and maybe a few hours with a big one. And as it takes time, there is this ongoing page that tells me the evolution of my current execution. So so far, we can see that it created three models, so 3 decision trees, 7 ensembles, 3 deep nets, deep neural networks, and 4 logistic regressions. And it's waiting to evaluate. So it will do a cross-validation with 3 training data sets and 3 test data sets. And when evaluation results are available, they will be displayed here as well. This will take time. So I already executed one yesterday. This would be the result after a few minutes. So this is how the result page, optimal result page looks like. So based on the metric I use, the raw KUC, in that case, the area under the curve, which is overall one of the best metrics to compare models, it is ordered to have the most performing models on top. So we can see from the icon is an ensemble icon, and in this case, it's a random decision forest with 129 nodes, and well, the parameters we can see here. Obviously, we can open the model and inspect it directly with the BigML page, so everything can be navigated very easily. So this is the ensemble page with the partial dependence plot, and we could see also the parameters that were used to create that ensemble in detail if we wanted. So we can, so here it is. Those are the parameters that were used, and we could just emulate that in production to have the best results if we trusted that. Again, I can also navigate to the evaluation. So I can see the evaluation page, just as we saw before from this ensemble. I can see a summary of the most important fields. So I can see here for this ensemble, it's a random forest. There will be the age is the most important field, the number of product and the balance, and the geography and the surname. Oh, the surname was not deactivated, which is my bad, it should be. So this tells us that somehow there's the behavior won't be that good in the end. So we shouldn't trust it anyway. However, well, we can see the surname, it takes importance. Even here, it's in the fourth position with our second data set. So yesterday when I did the test, I didn't remove the surname. Well, whatever. We can see also, let me filter per model. So we have ensembles are taking the top 10. I could filter and see, visualize more. We can see even the top 50, this is a deep net. But mostly ensembles and a deep net, and I could select by the algorithm kind, and we have ensembles are on top with 86% of rock AUC, and then the deep net is close. The best deep net is close, and then the decision tree is not doing bad at 0.83 as well. What we could do here also is maybe selecting different models and comparing, as I showed you before, seeing the evaluation comparison. So here the logistic regression is doing really bad. It's another classification algorithm, and in this case, it's doing much worse than the others. By clicking a button, we could see the evaluations compared in the screen I showed you before. So we can see the red one is the logistic regression and it's doing much worse, and the deep net and so maybe we could remove them. Decision tree is doing worse. The logistic regression is doing worse, and we could have well, compare visually and also with the table to see in what cases they are doing better or not. So there's this evaluation comparison screen. Okay, and I think that's all. There's also the possibility to fuse models. So I could select maybe the 3 best models and create a fusion which would combine the 3 models, just for you to see. So maybe and I could add weights. So maybe the first would have a weight of 3, the second a weight of 2, and the last one a weight of 1, and then we could create a fusion that would be combining those 3 ensembles, and I could maybe combine the ensemble with the deep net and get maybe a more diverse and more stability in my model. Okay, so this just for you to really quick to see it quick. The visualization of the fusion will be a partial dependence plot as well. Okay, I think I can carry on with, because I have other demos. So this was my supervised learning demo. Let me go full screen. So as a summary, that's this is a little bit the workflow that we followed. So we split the data and we created a model and evaluated an ensemble and evaluated, compared evaluations, and then created an optimal to get the best configuration and algorithm model. So this was done with a binary classification, but it could also be done with a regression or with a multi-class classification problem as well. Okay, let me go to the next demo. The next thing I wanted to show you is anomaly detection, and Professor Tom will be giving a chat about it later. So in theory, you'll get the details later, I think, but just to summarize really quickly, anomaly detection is an unsupervised algorithm that looks for unusual instances in the data set. And in general, anomaly detectors provide an anomaly score to each instance. The highest is the anomaly score. The higher is the anomaly score, the most anomalous is the instance. Here's a very simple example. So we have bank transactions, a very small data set. And we could imagine that the red instance, which has a very high amount and a different zip and class than all the others, could be considered as an anomaly over that group. Okay, just very quick as an example. You'll see the demo later. So the demo is about credit cards fraud detection. So we'll have a data set with credit cards transactions, and there will be a time column and an amount. And then we'll have the class at the end, which 0 means no fraud and 1 means fraud. And then we have 28 fields that are somehow encoded to numeric. We don't know what they are. They are complex fields, probably coming out of a principal component analysis, okay, PCA, not important. So we need to ignore the interpretability of these fields. We need to imagine that those fields somehow represent data from the bank about the credit card transaction. Obviously, this data is confidential and they couldn't share it as it was. This data set is from Kaggle. And then that's why they probably somehow encoded the data numerically, so that we have those numbers, 28 numbers that represent every transaction, an amount, and then a class. And we would like to find, using an anomaly detector, find fraudulent transactions. Let's see how the data set looks in BigML. So this is it, this one here. And it's how I showed you. There are so 31 fields. The class is the objective field, and we can see that we have 8,648 transactions, and only 30 of them are fraud. So the data set is extremely unbalanced, and with a data set that unbalanced, using a classifier to classify fraud wouldn't be good enough. So it wouldn't give good results. That's why we use an anomaly detector to classify transactions over fraud. Okay, those are the distributions from the 28 fields. We don't know what they are, but generally they would represent the data. And what I will do now is configuring an anomaly detector. I have different parameters. Professor Tom will explain what isolation forests are, but BigML algorithm, so BigML anomaly detection goes through isolation forests, and you can configure the amount of trees, and here, for example, we could configure the amount of anomalies that will be displayed in the output. There are different configurations. So all I will configure now is an ID field. So I want to create an anomaly detector, but obviously my objective field, this is an unsupervised algorithm, and my objective field shouldn't be used to detect anomalies. I want to detect anomalies without knowing the class, and then I will use the class to check if the anomalies were detected well. So if my fraudulent transactions have high anomaly scores, that's my objective. So for that, I will use the class as an ID field. So it is not computed inside the anomaly detector, but it is still displayed in the results later. Okay. Let me create this anomaly detector. Now it is building decision trees to isolate. So this is the isolation forests, building decision trees to isolate all the instances and several trees with random diversity in the trees. And then the easiest within the trees, my instances are isolated, the most anomalous they are. So in the end, the anomaly score is determined based on how easy it was to isolate the instances. Okay, so here, this is how the BigML isolation anomaly detector view looks like. In this case, what we see on the left is that you can see that we see 10 little squares. Every little square, little rectangle represents an anomaly. So the top 10 anomalies in my data set are represented here. Okay. And for each anomaly, you can see is the anomaly score. So my top anomaly has a 71.78% score. And I can see the field importance over that score. So I can see that the field V2 was the most important in that instance to determine its anomaly score, etc. And then I could move, and you can see that if I go on the right, I'm inspecting the details from my instance. So my top one anomaly has a very low V2. You can see it in orange here. it has a very, very low value compared to the whole distribution. It's really on the bottom. It's very extreme. And also V1 has a very low value here. It's also on the bottom. V4 has it's also on the top of comparing all the distribution. And V15 is also quite high. So, and then we can see the distributions for other fields. Even we have V19. So this instance, the top one instance, is very, very extreme. And we can see, if we go at the bottom, I can see that the class of that instance, however, is that it's not fraudulent. It's not a fraudulent transaction. The one that represented as my top anomaly is not a fraudulent transaction. Then if I go to the second one, I could inspect in the same way. The second one has a V15 really on top. The V3 is very low, and so on. And I also can see for the second instance that it's not a fraudulent transaction. However, if I go to the third instance, you can see that it is a fraudulent transaction. So I already managed to get my a fraudulent transaction in the third instance. We could see maybe what brings fraud. So we can see that V12 for my third instance is very low, V17 is very low, and V4 is quite high. The three most important fields. And for my fourth instance, if I go to see the class, it's also a fraudulent transaction, and my fifth instance is also. So I have 3 fraudulent transactions already. Again, I have V12 here, so V12 might be important for fraud. And in number 5, I also have V12. So V12 might be somehow important to determine fraud. That's something, an insight I could get from that, but well, it's a bit speculative so far. And then if I go down to see my 10 instances, so number 3, 4, and 5 are fraudulent. You can see it here. And number 6 is not fraudulent. Number 7 is not fraudulent. Number 8 is not fraudulent. Number 9, neither. And number 10 is fraudulent. So I managed to get, out of 30 total fraudulent transactions over 9,000, I managed to get in my top 10 anomalies 4 fraudulent transactions, which in terms of distribution, it's great. So this looks great, but I want to see more. I want to see more results. So what I'm going to do, I can do a batch anomaly score. So this anomaly detector allows me to score instances, transactions. So I'll do a batch anomaly score over my training data set. As this is unsupervised learning, and in my training data set, I didn't use the. Oh, it's getting trouble to find it. Okay, credit card. So in my training data set, so to create to train the anomaly detector, I didn't use the class. So it can be also used to evaluate as a test set, as it didn't have information about the class. I'm just going to verify if my anomaly scores match the fraudulent transactions. My high anomaly scores match the fraudulent transactions. So here, let me rename the data set. This would be my data set name. And now what it's doing is that it's assigning a score to each one of my transactions based on that anomaly detector. So my original transactions, almost 9,000, with all the attributes they have, will now have in this data set an anomaly score at the end. You can see this is a new field, the anomaly score. And I can see the distribution, which looks good. So we can see that high scores are residual, so there are not much high scores. And I could somehow filter high scores to see if they correspond to fraudulent transactions. Let's see that. Let me filter. This is in the data transformation menu. I can filter by score greater than 0.50. And I'll rename the data set to recognize better. Score greater than 0.50. And then I'll have a small data set, a smaller data set, only 173 transactions with an anomaly score over 0.5. And what's the distribution of fraudulent transactions? So I have 27 fraudulent transactions within my top anomalies, and it's really, really good. Okay, we can visualize this. There's a tool to visualize data sets, the dynamic scatter plot here. And we can visualize, we can plot the data based on 2 dimensions. So we have the score on the Y. Let me remove that. Sorry, let me remove the here. Okay. We have the time on the X. It's not important for us, and we'll color based on the class. So the orange ones are the fraudulent transactions, and we can see that based on that over 0.55. So I could filter over 0.55, and I would get the 27 fraudulent transactions that I managed to get already. And this anomaly detector seems to work really well to detect fraud with those attributes. Actually, it seems to work too well. It's too much. I wouldn't believe it. I think there might be, so there's something in that this data set is from Kaggle, and there might be a PCA. They might have used a PCA to anonymize all the data, and they might have left the class inside the PCA. That would explain why it works so well. It's not normal usually. It needs more work, believe me. Okay, so well, as a summary, what we did is, so the idea here would be training data with historical transactions without fraud. We would train an anomaly detector, and then new transactions would be scored over the anomaly detector, and we would keep high scores and somewhere and give those to fraud analysts so they could determine if really the transactions were fraudulent or not, and do their work in that sense. So in general, what we did now is classification. So we had a very unbalanced data set, and we used an anomaly detector as a classifier to classify fraud or non-fraud. But exactly the same could be used with other use cases. So for example, if we have typically unbalanced data sets happen with predictive maintenance to predict errors of machines, or in network intrusion as well. And the same procedure could be used. So it's often the same approach. I had another small demo, and then there are use cases to go through. I think I'll show you quickly association discovery, and then I think it's quite quick, and then I'll go through the use cases. So association discovery is another unsupervised method that in BigML, and it looks for coincidences into data, and the return are association rules with an antecedent and a consequent. So in general, it's very useful for data exploration and can have other utilities. So if I look into my data here, I can see, for example, that when Bob and this account happens, more often the zip is that, and when the class is gas, the amount is maybe under 100. So these rules are found by the algorithm, and they have an antecedent and a consequent. So when this happens, then this other thing happens, and then there will be some metrics. We'll see it in a bit. Okay, so really quickly, I wanted to show you the data set first. So the data set that we're going to use, it's about market basket analysis. So it's about exploring in a shopping business, in an online shopping business, we have every purchase recorded and with the number, the order number, etc. But in the end, what interests us is the list of products that were bought in every purchase, that are kept here in text, because you can see that there are separators, so that those will be considered as items within BigML. Let me show you. So I have my data set already loaded here. This data set is quite big, so I won't be running the algorithms live. So you can see that there are 3 million purchases, and we have the different fields, and the one that interests us is the products. So the products that were bought that are as an items type. So an item is a list of items, and we can visualize. Oh, okay. Yeah. So there are only 30 minutes remaining. Don't worry. So we can visualize the items with a word cloud. So we can see that there are a lot of bananas, or bag of organic bananas, or organic baby spinach. I think the shop is an organic shop, because everything is organic mostly. However, so from that, what I could do is creating an association discovery to find coincidences on data. And in this case, I want to find what things are being bought together, what items are being bought together. What I can tell them for that is forcing the consequence as one of the fields, because I don't care about the others. So I want my consequent to be products field, and I want only to consider as inputs the product fields. So I will see what products correspond to what products as a consequence. And then I would create the association discovery. This, as I said, it's a huge data set, so it will take time, but I have here some executions, former executions. This is one. So after a few minutes, this is how it looks like. So that we have the rules with the antecedents. Let me zoom a little. We have the rules with the antecedent and the consequent and different metrics. Okay, so for instance, here it is telling me, when people buy blackberry cucumber sparkling water, they also buy kiwi sandia sparkling water with those metrics. Okay, and those metrics represent, for the coverage represents the percentage of time where the antecedent appears. The support represents, and it's written here, it's intuitive in terms of it appears if you have dots later, but it represents, so the support represents how much both the antecedent and the consequent appear. And the confidence is the percentage of confidence for the consequent when the antecedent happens. So based on that, I can know that when people buy blackberry cucumber sparkling water, they will also buy, they're mostly, so they seem to buy sandia sparkling water 28% of times as well. So yeah, there are rules taken out of that are given us insights based on the purchases. And just for you to see that there's also a graphical visualization. This would be too much, but maybe you here, I can filter the leverage, and well, I could see that maybe. Okay, so that we have products here put together by couples, or by here we have something more complex. So there's a way to visualize as well the connections between products that are bought more visually. That can be interesting. So just for you to, so in this way, you have seen the whole supervised learning capability, not the whole. We didn't show other models or time series, but most of it. So you've seen model decision trees, ensembles, and optimal. As unsupervised, I showed you anomaly detectors, and I quickly show you association discovery, which is very useful to find insights and explore data. So you have a little overview. There are other unsupervised functionalities, such as clusters to group data by similarities, or topic models to explore text, and also principal component analysis. And well, BigML has further capabilities. I only show you the dashboard. I didn't do any API demo. There are also, all this can be done through the API programmatically. And well, I think you have now an idea about what BigML would help you do and how it looks like. Remember that there's a bunch of documentation, detailed documentation, and in general, any doubts can be addressed quite quickly. And there are a lot of video tutorials. And we also have personalized education programs if needed for a better machine learning adoptions, often in customers. So let's go for the use cases. I think I'm a bit late. I'm a little late. First, we have this slide where we have the typical use cases going on. So you can explore it in the PDF version. And well, I'll skip that one too. I think I'll go directly to the use cases. So this is one we have in Africa about churn prediction, and it's about a company that was providing electricity based on solar panel leasing, and the system would be prepaid electricity, so the customers would load their system with money, and then they would get electricity from the solar panels. The problem with that is that there were many cancellations, and the usage and payments were erratic. So, and the cost of a cancellation was expensive because they would lose the solar plate and the loading device, and then it would be 100 times higher than paying to retain a customer. So they were really interested in predicting churn to marketing retaining customers. The data used for that was customer profiles historic usage patterns and payment behavior. And first, what we did was doing a cluster, using clusters to segment for a customer segmentation to group customers by similarity, and then a classification, as I showed you in the demo, for churn prediction. And the results were very satisfactory, and they integrated, and they managed to reduce 90% the cancellations. Okay. Another use case, also very successful, is about a call center. So in this case, it was a call center that was devoted to charge returned bills from a telecommunications company. So every month there would be some returned bills that would return to the telecommunications company, and this call center would call all the customers so they would pay their return bills. The idea here is that they were using human and also automatic callers, but the machines they were not able to go through all the calls. So the idea is targeting the calls, so predicting whether each bill has a probability to be paid or not, and using that KPI in the prioritization of calls. So what we did was using demographic information and historical bills information, and obviously the historical bills outcome as well. And based on that, very quickly with a classification model, the prediction, the outcome prediction of the bills was successful. So we also used association discovery to explore data, and in the end we used Optimal to get the best model. And for that, in the end, this was deployed in production simply just providing the probability for a bill to be paid to the system they currently use, and using that KPI as in the algorithm for prioritization of calls. And after a couple of months, we increased by 8% the monthly income of the call center. Another similar transaction also related with call center is about customer service, in this case, because the customer service call center that would be, in this case, it was about printers, fixing printers, so printers issues. And the case was that the customers called and there were issues that needed some presential support. So they needed a technician to go to the on-site and fix the printer, and other issues could be solved in the distance. And deciding whether categorizing the instance, categorizing the incident, so the call, into whether we needed to go or not, was really important as an efficiency outcome. So the idea was predicting based on the support case if the case needed an on-site or remote address. Okay, so the data used is were the printer characteristics, incident description, contract characteristics, and obviously the outcome of the past historical case, if it was on-site or remote. And based on that, we first used topic modeling, which is an algorithm taking topics out of text. So as incidents are sent via text, topic modeling was used to tag the incidents based on the text that included, and those tags could be used as part of the classification attributes. And that classification was used to classify the incident as remote or on-site. The classification results were successful, and we managed to deploy this in different countries. And the idea of that is growing, and maybe in the end, automating the whole process. No? As we said before, machine learning is compositional, and this could be the first model, but then we could improve and in the end, obtaining an automated bot that would solve cases automatically. In manufacturing, this is another project we did. It was about a film metallization process. So those kind of machines, we had a big roll of plastic film, similar to the kitchen plastic film, but really huge, 20,000 meters. and 1 meter wide. And it was put inside the machine, and then the machine would run for 40 minutes, and metal would be evaporated over that film. And then that film would be used to build condensators. So those executions took 40 minutes, and we had a lot of parameters, a lot of information coming out of the machine in real time. The problem is that, well, if the outcome of the process was not good, then a big part of the role couldn't be used, and money was lost. So the idea was to optimize the outcome of the manufacturing process. And in that sense, during the execution of the process, we would like to predict whether the execution would be successful or not. So for that, we used historical executions, which had data from internal and external sensors, and also the parameters before launching the execution. And also, as an objective field, somehow, we had the quality assessment results, where we had the real results of the outcome of the process of the execution. So based on that, we used classification. So first, association discovery to explore data, and then classification was used to predict in different moments of the execution what would be the outcome of the process. On top of that, an application, predictive application was delivered with a lot of visual inputs for the operators of the machines to simplify their life. And well, there were second phases on that, because typically in manufacturing, it's very useful to use anomaly detectors as well to detect malfunctions. And a next phase for that project could be using anomaly detectors to find malfunctions in different components of the machine beforehand. That's another use case, which was about more in the legal aspect, to predict NDA signatures or non-disclosure agreements or contracts that need to be signed for confidentiality. And apparently, I don't know much about it, but apparently they are very mechanical. So they are the analysis of those contracts is kind of mechanical. However, it takes time. So the idea here was automating the analysis of those contracts. That was implemented by Jury Blocks, so those are legal experts, and also implementing technological bids for legal matters. And they implemented NDA Lean, which is a tool that is online and that allows you to analyze an NDA and tells you the errors by detail. For that, what they used is a bunch of NDAs already somehow tagged with their metadata and prepared to train, with all the insights and that could be extracted. And then classification algorithms were defined to extract the different insights. So in the end, there's a paper about it, and the contract is being divided by sentences, and every sentence has a tag determined. And in the end, they look at the tags that exist at the end of the analysis, and maybe find missing or missing clauses, or maybe wrong clauses. So that's there are 3 classification levels, and making 3 classifications, they allow you to give you first if you need to sign or not, and then they give you the different alerts within an application that is very simple of use. That's another also financially related. So this is more in accounting. So I don't know if I did accounting. I mean, from my accounting experience, it's kind of repetitive as well. So we need to determine some categories for every kind of transaction. There are 2 levels of categories, and it seems kind of repetitive and mechanical. So based on the idea here is automating that arduous process, and the idea was using historical accounting transactions already categorized. And based on that, we would have, as there are 2 levels of categories, we would have 2 levels of classification to categorize new accounting transactions. And all this was implemented this was for Anfix, so it's a Spanish company about finance, and it was implemented in their application. another interesting point, and I think I'll stop shortly to leave moments for the questions. But another interesting point is about credit card fraud detection, and this was used only for with anomaly with association discovery. So in this case, we wanted to find the credit card fraud origin. This was done in Colombia, and they had some cards were copied, and they wanted to find where they were copied. And in general, so if we got fraudulent transactions and the previous transactions from the fraudulent transactions, we could see that there might be a transaction within a place where other other cards with fraud would also have been, and they might have been copied in the same place. So the idea here is using, based on fraud transactions and their history, using association discovery to find commercial places where the cards were used before the fraud. And we could, based on that, return a list of suspicious places where the card was copied. Well, there's a bank fraud detection case. It's very similar to what I showed you, and they're using it at Rabobank. There is in the last slide there is a video about it. So there is also fraud detection for Seagates in their returns for their warranty part. So they have returns for the drives, and sometimes fraud is used to returning those drives, and they use machine learning based on historical data with anomaly detection to find and spot fraudulent transactions as well. This is about chemistry, or chemistry process. So I think I'll stop. I think it's I gave enough use cases. I'll go to the final, to the end of my presentation, so we can have a few minutes for questions. So machine learning, in terms of machine learning adoption, there is a curve where business need to go through to adopt machine learning. And it starts in general, so the big tech companies are on top, so they have predictive apps, and everybody in the organization is using machine learning. But everything starts by using probably point and click access, as you have seen in the dashboard, and maybe starting from a user in a department and then growing into multiple users in one department, maybe multiple users in multiple departments, and then reaching everyone in the organization. And all this with a BigML solution, or I mean, it could be it is driven starting from the dashboard and programming, and there's this other curve where we can see that initially we would have there are no machine learning based processes in the company. Then there would be a little machine learning used, and step by step helping to adopt machine learning more and more. And those simple machine learning tools help business people, but also technical people in the company, adopt and bring machine learning and help productivize. So in the end, by using those simple tools, it's more easy to get more models in production and to put together the business team with the technical team, which is something interesting in that sense, because the business team needs to make decisions based on machine learning as well. So a good example, I think I didn't explain, I explained really quickly, but a real good example is explained by Jan Belzing from Rabobank I think it's about 25 minutes. And he explains really well how well it worked for them to adopt machine learning from the business perspective at Rabobank to do fraud detection with BigML. And well, it's quite interesting. If you have doubts about that, I think it's a very interesting chat. And well, and that's all I wanted to say. I hope you enjoyed it, and now it's time for questions if you have some.
Okay, thank you so much. So if you have any questions, you can just raise your hand or type it in the chat box. If you raise your hand, I don't mute you and you can ask the question directly. We have a couple more minutes before this session is over. Thank you to DSN for increasing the time that we have. Okay, so please, any questions? Any questions? Any questions? Okay, there's one from Olanrenwaju. He's asking, how can we deploy the ML models?
Okay, I was muted, sorry. So, so once you create a model, in BigML is in the cloud, and the models I have in my, let me show you the platform here. So the supervised models I have here are already deployed somehow. So they are now in the cloud and they can be used for predictions. If I have an API, I could point to that model. It has a unique identifier, and my API, I could log in using those privately, using those credentials, and I could very easily make predictions over that model. So to put models in production in BigML is as easy as creating models, because models are available there. And then you just need your production system to make predictions over those models. Obviously, it's a bit more complex than that, usually. I mean, you will need to implement something. You will need to implement an application and to change the implementation in your application, so, and gets the input of the prediction every time. But mostly the models you see in BigML, the models I created with a few clicks before, are already in the cloud and they are already available to make predictions. Also, another part, so if I go to the ensemble, for example, so here I have my ensemble. I can download actionable ensemble. So here I could see what the code looks for the API. So this is a code, few lines of code, really 4 lines of code using the API, where I would be exporting my ensemble locally. So I could be using this from the web, implementing those lines of codes from a different system, a remote system that could be maybe in a clock or in a factory, and in a factory machine, for example, and putting using those lines of codes, the model would be downloaded as a JSON, and with the API, that JSON would allow to make predictions. So it's with a few lines of code, it's possible to implement that model locally. So let me show you what the JSON looks like. So if I go here, this is my ensemble. This is the JSON of my ensemble. You see, it's a bunch of text, and this text, if I move it, if I copy and paste this into any machine where I have the API installed, I can make predictions. So this is another way to make predictions locally. I hope I answered your question.
Okay,
we have another question about can you automate jobs to run on new data, for example, pre-processing steps? Do you want to talk about that one, Guillaume?
Yeah, again. So so yes, you can. So in general, in BigML, all the resources are immutable. So if you see, I cannot change my ensemble. I cannot modify it. If I want to train with new data, I would need to have new data and create a new ensemble. So based on that, obviously with the API that we have, it's very easy to automate. So we would need only a flow of data and then create another model with the new data, concatenate the old with the new data, and create another model, evaluate it, and if it's better, then we get the best one. We keep it in production. We change the reference in production, so it points to the best model, for instance. And another way is that we have what we call WizML. So WizML is I didn't speak about it in the presentation, but it's a proprietary language that allows you to generate and to create workflows. And the resources are immutable, so I cannot modify this ensemble, which in general could be thought as something bad. But the good thing about that is that what I reach to get this ensemble is traceable. So I could, even if I did 100 steps with data transformations in my data set and many other things, with a single click, I can reproduce the code that I just did. It is here, scriptify. So I could scriptify the ensemble with a click. And this ensemble had a few steps, maybe the split of the data, the training of the ensemble. It's not complicated, but maybe imagine it was a very complicated model. So maybe I had anomaly detectors first, and then combining it with clusters and many other things. And then with a single click, if I go to a resource, I can generate code. So this is the BigML code. It's Lispy code. Okay, but well, you don't need to look at the code. I mean, even if you don't want to code, you don't need to, because this script has this code, and you can modify it if you want. It's documented, and then we can. And now this is an execution where it's asking for me for a source. So the source obviously needs to be have the same format. But now I choose my source, and I execute my code, and automatically, without doing anything, it will do exactly what I did before. So you can automate things with BigML as well. Okay, I hope I answered. So there are many ways of automating jobs, most through the API, as you saw a little code for the ensemble. And there's also BigML to visualize clusters. So the BigML, we can see the executions here. So now this is my execution I just did now, and I can see the result of my execution. So there's an ensemble resulting, a new ensemble that was just created. If I go to the ensembles, so there's this ensemble that was created 0 minutes before by my script that I created without touching any code.
Okay, we also got several questions about what support there is for deep learning.
What support there is for deep learning. So in deep learning, what we have at the moment are the deep nets, but those deep nets are not convolutional neural networks, and they are not useful so far for image processing or for natural language processing. They are just basic neural networks that are used for classification and regression. However, as I said during the chat, the next release will be about image processing and will contain convolutional neural networks, and very simple. It will be very simple to implement image processing projects, image recognition. So that would be the coverage we currently have for deep learning. So I can see one question here. With high rate of automations happening in the industry, what is your advice to average data scientists, machine learning engineers, etc.? Also, what is your advice in language learning path for future data science? So that I think that do you want to address that one, Professor?
Well, I guess I'm doing a mentoring session in another hour, I think. I think that if you were a data scientist in a company, that you could probably do 80% of your job using BigML. But I think there's always a need to be able to code your own information around BigML. So I think today you must know Python, right, to do data science. And then from Python, you can call the APIs for BigML or for other things like PyTorch or TensorFlow. So I think you really need those. I also think it's good to know one of the I guess, data science packages like either R or Pandas. I mean, you can do a lot of the routine stuff that you would do in R, Pandas can be done in BigML more easily. But sometimes you need some custom thing, and then you could either write a Python wrapper around BigML or code something up using Pandas or R. So I'd also say that I think I'm seeing a big need for people who have more of a systems background as ops, that is, continuous retraining and delivery of improved versions of ML systems is now becoming really a critical thing. So finding ways to keep the cost of ownership of a deployed ML application, reducing that cost is now really becoming mission critical, I guess, for for machine learning engineers. It's actually can be sometimes harder to, after you've deployed something, to keep it up and keep it running than it was to build it in the first place, just like other software. So.
Great. I think all the questions have been answered. Any other questions?
Okay. Thank you so much, Professor. Thank you so much, Guillaume. Please, let's give them a DSN appreciation. Put in the flex emojis, all the fire, all the appreciation. Awesome, awesome. Thank you so much. Thank you so much. So this is the end of this breakout session. Yes, yes. Please, let's keep the flames coming. Thank you so much. Appreciate them. Thank you, thank you. So this is the end of this breakout session. We'd be going back into the main room. We also have another session, as Professor has mentioned. There's also a one-on-one career talk with him in another hour. So prepare yourselves. I'm seeing you're already excited, so please come prepared. And thank you so much once again for staying in the session. Thank you, Professor. Thank you, Guillaume. Thank you so much. So we can leave this and go back to the main room
Thank
now.
you.
Yes,
Thank you
yes.
for having us.
No problem. You're very welcome.
Take care. I'm stepping out. Huh? It's the moment to step out, right?
Yes, yes. You can leave this session now. You can go back to the main room.
Enjoy the rest of it. Bye bye. Thanks.